Hello, everyone, and welcome to a new session of Surfing the Ocean. Today, we have the pleasure of meeting Mathieu Molina, who's a PhD student in the supervision of Vianney Perchet, who's gonna talk a little bit on equitable auctions. The floor is yours.
Thank you very much, Antonio, and thank you very much for the invitation. I'm very happy to be here. So today I'm going to present your work we did jointly with Simon Finster, Patrick Loiseau, Simon Moras, and Barry Pradelsky on notions of equity in auctions. And these are the slides of Simon, and I modified them a bit. So if you see anything which is bad or if there is any mistake, it's on me. So the goal of the presentation is I'm going to give you first a very quick crash course in auctions, like try to explain why we care about auctions and like some preliminary results. And then I'm going to get into a bit of the motivation, and afterwards I'm going to get into the specifics of the paper. So first of all, very simple question. You're a seller with some items to sell, and what should you care about? Very broad question. So one thing you might want to care about if you have some items you want to sell is a notion of efficiency. Maybe because of the government, maybe because of regulations, you want to give the items to the people that value it the most. In some sense, to optimize some kind of global social welfare, right? So if you have two person, let's say Antonio and me, I value a new pair of sneakers at 10 euro, Antonio values it at 15, we want to give it to Antonio. And Antonio is going to be my example second, second bidder for the presentation. So this is one aspect you might want to care about. But of course, one other aspect you might want to care about is revenue. If you are a seller, if you're an auctioneer and you want to make money, you want to make as much money as possible. And so this is a question of when you are going to sell your items, the payment you're going to receive, you want to maximize this. And this is how can you maximize this payment and what is achievable in some sense, right? So this is two concerns. And basically, in this paper, we introduce a new concern, which is about equity, right? And I'm going to be a bit vague, and I'm going to give more formal definitions afterwards. And you want to be equitable among the buyers, meaning that the people who are going to participate in getting your item, they're not going to think that the mechanism is unfair in some way. So why do you want to care about equity in auctions or in other mechanisms? So it's for reasons of market stability and competition, right? You want to have a healthy competition, so to have like a healthy, fair or equitable outcomes. Just maybe for ethical reasons, you want to be fair, and also it can be for long-term incentives for participation. Like if you participate to some kind of mechanism or auction and you think that the outcome is unfair, you might not want to participate again, and you might decide to go some other ways. So some example of applications can be like, or reason why you want to care is EU regulations, spectrum auctions, where you basically sell radio waves for radio stations, or like small business concerns in procurement. Okay, so this is kind of the motivation, pretty broadly. So now let me give you the quick crash course in auctions as I promised. So we're going to first look at a very simple model for me to introduce auctions, and then the model of the actual paper is going to be a bit more complicated. So we have a single item to sell and bidders, so people who want the item. And we're going to assume that each bidder has a private valuation VI, which is drawn IAD according to some distribution F. So by private, I mean that I know that I like my item, value my item to be around 10 euros, but I don't know how much Antonio values the item. Like this is private information, but I do know, like I have a rough idea. I know like he's likely to have this and that value, and so I still have some Bayesian information basically about the adversary. And so this is like the classical setting in auctions. And when I win some item, I'm going to derive some utility or some profit, which is simply my value minus what I'm going to pay for the item. Okay, so very simple. And if I don't win an item, I obviously going to have a utility of 0. So how to achieve efficiency? So maybe the first thing you could think about if you've never done any game theory is you just ask people the value and you give it to the highest value, to the person who claims to have the highest value. And of course, this is not going to work because, as I've said, like you're going to give to the person who claims to have the highest value, and basically everyone is going to lie. For the pair of sneakers, I'm going to say, oh, actually, I value this pair of sneakers 1 billion euros. So, if you want to maximize social welfare, you better give it to me. So this is one example which shows that when you're going to consider agents who strategize, you have to be careful about the kind of mechanism you implement. And this is like a lot of the consideration about mechanism design is how do you choose the rules of your game in such a way that you achieve your desired outcome. So in this case, the desired outcome is to give the item to the person who has the highest value. And so one very classical result, very famous result, is of Vickrey in 62, who introduced, or at least formally analyzed second price auction. And so basically, the idea is that auctions are going to be a very good mechanism in order to give the item to the highest valuation. So here's the second price auction. It's like a sealed bid second price auction. So everyone is going to bid some bid BI, which is going to be private. Okay. So simultaneously, everyone bids something. The people who receive the highest bid, or the people who the highest bid receives the item and pays the auctioneer the value of the second highest bid. So this is why it's second price auction. Okay. So it might seem a bit weird to do second price and why not just pay what you bid? But this is, as I mentioned, a sealed bid. So it's not like the usual auctions which you can see, like let's say in television, etc., where you have people which raise the sign and say, "Oh, I'm going to bid 10 and then 15 and then again 10." Here it's the sealed bid auction, but they are actually in some sense equivalent. So if you imagine that you have like this raising price auction. By the way, if at any point anyone has a question, I'm very happy to interrupt and answer them. Like that's for sure. So if you have like the classical television auction, so everybody is going to raise the price, and basically if Antonio says, "Oh, I value, I'm going to bid 10 euros, and maybe this is his maximum value," there is no reason for me to not bid anything other than, let's say, 10 euros plus 1 cent. Okay. So effectively, in this case, if I'm going to win the item in the end, this is equivalent to the second price auction that I just mentioned. So this is just like a motivation. And so for all the rest, we're going to look at like simultaneous private bid auctions. So now we have the second price auction. And so a very important result is that being truthful, meaning that bidding your own value, so BI equals VI, is a dominant strategy in second price auction. Okay, and let me give some simple reason why. So if let Y be like the second highest value. Okay, if you have that the second highest second highest value is smaller than VI. So Y is going to be the second highest bid. Yeah. So second highest bid is smaller than VI. Then if you win the item, you get VI minus Y, which does not depend on your bid, and which is positive, and otherwise you get 0. So basically, you just want to win the item, and a specific value which does win the item is exactly BI equal VI. Okay, so among all the possible maximizers, VI works. Now, if Y is greater than VI, then if I get the item, I receive a negative profit. So like I have a loss of VI minus Y. And if I bid lower, I'm not going to get the item and I get 0. So if I want to maximize, I need to basically lose the auction. And so BI equal VI works. So in both cases, basically, I'm saying that among all the maximizers, bidding VI is actually optimal among the maximizers. And I have access to this information because I already know VI. So a simple strategy is going to be always bid VI, and this is going to work out. And so the second price auction is truthful. And this implies a very nice property, is if everybody bids their own valuation and you give to the person who has the highest bid, then you give to the person who has the highest valuation, which means that the auction is efficient. Okay, so now if we want to have an efficient auction, we just need to do second price at the time. So now let's look about the second concern. So what about revenue? So one thing you might want to do is you say, okay, I know auctions are good, but maybe I can get something better if I use a different pricing rule. So now I'm going to do a first price auction. So the winner pays the highest bid. And because if you win, you had the highest bid, you basically pay your own bid. So in sometimes I'm going to refer it to as pay as you bid. Obviously, this auction is not truthful because if you bid your own value and then you win the item and you pay your bid, then you get zero all the time. So clearly, this is not going to be optimal, right? And so now we're going to use some game theory to basically put some behavioral, not rational behavior assumption on the players. And we're going to assume that people play according to a bias-Nash equilibrium. So bias-Nash equilibrium is basically a function, a strategy, which maps your value to a bid. And we say that beta is a bias-Nash equilibrium if for all value and all possible bid, considering that everyone else is playing according to beta, so everyone follows beta besides yourself, you're better off by playing beta as well, in expectation when you've already seen your value, right? So it's like the conventional expectation of you playing beta when everybody else plays beta is higher than any other bid you could play. So this means that basically it's a fixed point result. So it's like a conditional expectation version of a Nash equilibrium. And this tells you, yeah, that basically beta is a fixed point, and it makes sense because you have no incentive to individually deviate from this strategy. Okay, so now we have this beta symmetric bias-Nash equilibrium. And there's a result which tells you that for symmetric first price auction, there exists a bias-Nash equilibrium, which is not necessarily easy. Okay. And this has this form. The specific form, we don't care about it, but just for the analysis, it's nice to have like a closed form. And when I say the existence is not easy to tell is, for instance, if you don't have symmetric distributions, so like you have independent but not identical signals or values, then it like the proof of existence was a big result. And there is no closed form for the first price auction, and we know that this is hard. Okay, so just to say that very quickly, deriving equilibriums in auctions can be quite tricky. But we have the good property that this equilibrium is increasing, meaning that the highest bid is also the highest signal, and so this auction is still efficient. Okay, and now what about revenue? There is a very classical result of Meyerson in the 80s, which tells you that any auction which is efficient and reasonable, I'm not going to get into details, have all the same revenue, where revenue is just the expected payment. Okay, so this means that we cannot do anything better if you want to remain efficient, and you have this whole class of auctions which basically have same revenue and are also efficient. So this begs the question is, okay, you want maybe to choose a specific kind of auction, so maybe you want to add another criterion to decide what kind of auction you want to pick, and the criteria we decided in this paper is an equity criterion, basically. Okay. So this was like the single item private value independent case. Are there any questions up until now? Now we're going to get into more of the specific of the paper. No questions?
Can you just repeat what you just said about the symmetry? Whenever there is no symmetry, so if it is symmetric, you have a closed form, a closed form solution. That is the one that you show. But if if you have no symmetry, also no
So
symmetry in the sense that symmetry on the utility that you use on the IID sample of your VI.
on the samples of the VI. So if I have a distribution F1 and you have a distribution F2 which is different, then it's hard to derive the equilibrium, because the way you derive the equilibrium basically is you use a first order condition, right? And you get a differential equation. And it so happens that when you have symmetric distributions, you can solve this differential equation. When you have non-symmetric distributions, you cannot solve this differential equation in closed form.
Okay. Okay, so it doesn't matter the kind of utility you have.
So if you use more complicated utilities, it gets even more complicated. But here, the utility functions are symmetric. Even if you keep the utility function symmetric, you're going to have a trouble with asymmetric distribution. But even no, I'm going to say, like if you take asymmetric utilities but symmetric distributions, you're also going to be in trouble.
Okay. Okay.
So
Thanks.
Most of the time in auctions, like if you deviate just a little bit too much from like the classical stuff, you're not going to be able to do anything in terms of like
Okay.
deriving the exact equilibrium. Okay,
Okay. Thanks.
no worries. All right, so this was a single item, etc. Now I'm going to think about a generalization of this, and I'm going to say, no, I'm not selling one item, but I'm going to sell multiple items. Okay, so a very simple generalization. And what kind of auctions I'm going to consider? So I'm going to consider a generalization of the first price auction, which is going to be the pay as bid auction. As I mentioned earlier, it's just basically you pay what you bid. And a generalization of the second price auction is going to be the first rejected bid. So, right, the second price when there was one item was the first rejected bid. And so you can still say the first rejected bid, even if there is like multiple winners. And you're going to make this payment for everyone who wins. So basically you have on one side a uniform price auction, which is based on the first rejected bid. And on the other side, you're going to have a pay-as-you-bid auction. Okay? And the colored area, so the red line here is the payment. And the colored area is going to be the utilities of each player who wins an item. And now we want, as I said, we want to care about equity. And the thing is, okay, if I tell you you are this guy, so the last one who wins an item. If you're this guy and you compare yourself to the first one, you're like, oh, he has a much higher utility than I did, and maybe you're kind of jealous of him. And so there is you feel that it's kind of unfair in some sense, right? And so now if you say, actually, if everybody had the same value, but you had played, instead of a uniform price auction, you had played a pay as bid auction, you can see that the difference between your utility and the utility of the highest is smaller. So in some sense, by equity, I mean, how is the surplus distributed ex post? Okay, once you've played an auction, how is the surplus distributed? And we're going to think about what kind of auction is going to give ex post surplus, which are ex post profits, which are as concentrated and as equal for all the winners as possible. Okay, so this is like the kind of the intuition about equity. So something we can try to think about first, and keep this in the back of your mind for the end of the presentation, is maybe you can just like look at the profit that everyone got, take it at the auctioneer and kind of redistribute it. So you take everything, then you make everything equal, But if you do this, obviously people, because they behave in a strategic fashion, they're not going to tell you their value. So for instance, when I tell you, oh, take the profit, you don't know the profit because you don't know their value, right? So it's not necessarily possible to do this. It's not obvious that it can be done. So you need to think about the design of multi-unit auctions for identical items that distribute bidder surplus equitably. Okay, and so like some keywords, so we have in multi-unit auctions, identical items, meaning that you can think about it as a supply, in the sense that like the items that you can win are identical. You don't get like more money from one or the others. We think about utilities and we think about equitability. These like some of the keywords. Okay. So the contribution of this work is in threefold. So first, we introduce some notions of equity in auction. Okay. Then we're going to give some prior free results on what do you prefer between basically pay as bid auction compared to uniform auction. Like what should you play? And third, we're going to say, okay, now if I can use actually any mechanism, any kind of auction, what is the best that I can achieve? So more of an like the second point is more of a comparison perspective. The third point is more of like an optimization over the space of auctions perspective. Okay. So I'm going to introduce the model, some equity measures, and then I'm going to talk about the results, right? So until now, any questions about the motivation, maybe? Okay, right. I mean, for me, it's like, yeah, sure, you can be equitable. It's reasonable, and yeah. Okay, so now I'm going to get into the more specific model. So we have an auction market with n bidders and k identical items, and we have unit demand bidders. So this is very important. This means that you can derive utility from only a single item. So if I give you a first PF5, you're happy. If I give you a second PS5, you don't care about it because you already have one, right? So this is this kind of goods we're thinking about. And the reason why we do this is technical considerations. It's because even for very simplest setting of multi-unit demand, there is no known equilibrium to derive. I mean, at least it's very complicated. So this is why the unit demand is the simplest setting you can think about when you want to do with multiple goods to sell. Okay. So no, we're not going to have values. We're going to have signals, which is going to give some information on your value. We're going to have IID signals drawn for some distribution. So the signals are IID, but the values are not. And we're going to assume that we have some model of value which is between private and pure common value. So we're going to do a convex combination, basically, between your own signal and an aggregate signal, which is basically the average of all the other signals, right? And so we do this convex combination through the parameter C. If C is equal to 0, then you get back to the pure private value model that we had before. If C is equal to 1, then you have a pure common value, right? Where everyone has the actual same value, but each people only see a part of the information. So when they bid, they need to take this into account. And this is more complicated. And we're going to keep the utilities simple. So just your value minus your price when you win an item and 0 otherwise. This is the model. So basically just we parameterize a bit the model and we just say, okay, I want to look at convex combinations between pure private and pure common value. And now let's talk about the auctions mechanism we're going to look at. And we're also going to do some mixing between pay as bid and uniform pricing. Okay, so we're going to mix to do a convex combination between the payment of the pay as bid and the payment of the first rejected bid. So basically between first price and second price. And so the payment is going to be delta times your own bid. So this is the first price part. And 1 minus delta times B prime, where B prime is the first rejected bid. And we're going to consider symmetric and monotone increasing bidding equilibriums. I want to emphasize that the equilibrium of the convex combination of the auctions is not the convex combinations of the equilibriums of the respective auctions, right? So we do need to derive the equilibrium. And then the second mechanism we're going to think about is truthful mechanisms, but I'm going to get back to this later on. Okay, so some comments, first of all. So I said that we look at increasing equilibriums, which means that the auctions are going to stay efficient. And this is crucial because it means that when you, if you imagine that you switch auctions, given some realizations, the people who win the item are going to be the same. Okay, if you win an item in a specific auction, you're going to win an item on the other auction, right? It's just your utility is going to change, right? Because basically the ranking of the signals is going to stay the same if you just apply an increasing function on top of this. So you have your signal SI, right? You apply an increasing function, which gives you your bid. And so your bids are going to be ranked only depending on the ranking of SI and not on the bidding. So everybody keeps the same items. And so for this reason, we are also going only to consider equity among the winners, right? Because people who don't win an item, regardless of the auction, they would have not won anything, right? So we care less about them. The considered auctions are also revenue equivalent, and this can be shown quite straightforwardly, so it's not very complicated. And the reason why they are revenue equivalent is because even though the value is common, the signals are independent. If you look at the pure common value with dependent signals, then the revenue of the first and second price might not be the same. But here in this case, because we look at a specific model, this is still true. Okay. And so, as before, as in the introduction, do you have a question? Yeah.
Can you develop on why this happens for this model, but is not true in general?
Right. So you can have let's say affiliated signals or something more complicated than just independent. And basically your behavior depends on the signals. Like what you bid
Okay.
depends on the signal. So if the signals are independent, the behavior of everyone is independent.
Okay.
Whereas if the
Okay.
signals are dependent, then the behavior is going to be correlated, right? And this is why you have revenue equivalence. I mean, this like you have to get into the technical proof, but it's the fact that the bids remain independent because the signals are independent. But
Okay.
the utilities are not independent. This is like
So
a
basically, like everybody's independent, like in the way they behave, but like the thing is that you just correlate everyone with respect to their utility. Am I right?
exactly.
Okay. Okay.
Exactly.
Thanks.
Okay. And so in this auction space, no, we have the same as before. We have efficiency and we have revenue equivalence. So we know we're going to care about equity. I just want to, this is just to say that even if you go like to multi-unit items and to like this mixed common value, you still have this, you can still focus only on this. So let's talk about the equilibriums. This is not the most important stuff, but so first of all, important thing, if you are in the pure common value model, the second price auction is not truthful anymore. So you have this weird equilibrium, which is the expectation of your value, given that your signal is your signal, and the highest and the first restricted bid is also your signal. So this is intuitively a bit weird, but I'm just going to give some insight on why you need to have an equilibrium, why it's not truthful. Imagine you have a pure common value, okay, and everybody plays truthfully. So everybody has a some part of the signal, right? And so if you win the auction, this means that among everyone, you overestimated the most the value of the item. And so if you're truthful and if you win the item, you're actually going to lose money for sure. Because it's called the winner's curse, because it tells you that you actually like compared to everyone else, you overestimated it. And so you need to take into account the information of everyone else, and this is why you have this equilibrium. Okay, so you have an equilibrium even for second price auction in the common value case. And so now for a specific value of C, but this is going to be like a building block of the equilibrium. So I'm calling this equilibrium V for the second price for any common between private and common in my model. And now oops, sorry, whoop. I didn't think it would do this. Yes. So the equilibrium now for a given amount of price discrimination delta is going to be the following. Once again, the particular form does not matter. It's just that we're going to be able to extract some moneticity properties on this with respect to delta, and this is what matters, right? The exact form doesn't matter, but it exists and we can express it. And of course, it makes sense. Like if you apply a dominated convergence theorem with respect to delta, you can see that this converge when delta goes to zero. So when you go to uniform price, you get back the equilibrium of the uniform price. Makes sense, right? And when you put delta equal 1, you get back the equilibrium for PSB. Okay. So to give a sense of what these equilibriums look like, so here are multiple graphs. Okay. So you see that here, like for pure private value, so as I said, you're truthful if you have if you're in the second price case or the uniform case. And as you're going to add price discrimination, you're going to be often concave in some sense, right? So you're going to bid less in the sense because you want to extract some utility from this. And as you increase the common value part, you're going to see that you basically raise a bit your estimation of what you should bid as the common value part increase. So one very weird phenomenon is if you have multiple items to sell and you're in the pure common value case, you should actually bid more than you signal when your signal is zero. Okay, which is quite weird, but it's basically because you have multiple items to sell. If you have only one item, this is not the case. Okay. This is what it looks like. And so now we're going to talk a bit about equity measures. So maybe one simple thing, me coming a bit from statistics, you'll have like a vector of you have a vector of utilities basically among the winners, and you're just going to take the empirical variance of this. Okay, and maybe this is a good equity measure, and this is what we're going to use a lot. And I'm just rewriting the this empirical variance as the sum of the pairwise difference, right? Because I'm going to make the connection with another equity measure afterwards. But basically, this is this is just the expectation of the empirical variance among the winners. Very important. Okay. So here's some examples. So let me say first, yes. So first, let me say that unfortunately you cannot use revenue equivalence directly because the utility among the winners, even with pure private values, are dependent. This is not like, if you look at the utilities not among the winners, they are independent, but among the winners, they are independent. Because for instance, with uniform price, if you have Antonio who won like an item for a very low price, I'm calling you for a very low price, I know that I'm going to get a huge utility because the price is going to be the same for me. Okay. So in this case, I have some kind of positive correlation among the winners. So we cannot just like expand. Basically, I'm saying we cannot just expand the sum and like get something out of it. And actually, you can express these winners' empirical variance as the variance of the utility among the winners minus the covariance between two signals, two utilities among the winners, right? And this is symmetric, so it's just like it doesn't matter one or two. You can like take the average of the n. And so a very small small result that is not related to this, but we also show in the paper that actually with pure private values, the pay has been minimized just the variance of the utility among all standard options, because it's just an aside. But the variance of the utilities is more of a risk measure than an equity measure, because it doesn't depend on what others receive, right? So this is what like this covariance things really highlights why it's different from just the variance. And so now we're going to just look at the winner's empirical variance for different values of C and delta, see if we can get some intuition, and then see if we can try to formalize this intuition. So let's look at the case where we are in the pure private value case, okay? And this is going to be the blue curve, and we can see that as I go from uniform to pay as bid, it looks like my winner's empirical variance is decreasing. So maybe this says that when I have pure private value, I'm better off having a pay as bid auction rather than a uniform one from an equity perspective. Okay, this is first intuition. Second intuition, when I have pure common value, okay, so this is this brown curve here, I see that the winner's empirical variance is lower for uniform than pay as bid. Okay, so second intuition, maybe for pure common value, it's always better to play the uniform compared to the pay as bid. Second intuition. Third intuition is if I look at some intermediary value of common value share, it looks like the minimum is actually some intermediary delta. Okay, so this says that maybe for some range of C value, then I have it means that basically mixed pricing is useful, because if it never happens, then I'm better off just not thinking about mixed pricing at all. Like if it's always worse than either pay as bid or uniform, then it's useless. But in this case, maybe this shows that it's useful. And now we're going to see which intuitions hold true, to what extent, and if it does. Okay. I'm going to introduce a second equity measure, which is going to be useful and maybe and maybe stronger. If I look at a specific vector of utilities between two different auctions, I say that the first vector dominates in pairwise difference the second vector if the absolute value between all elements of the vector than the other vector. So basically, I'm saying that the dispersion of the utilities is smaller in the first one compared to the second one. Okay, and I'm going to say that why is it very strong? It's because it's a partial order. No, sorry. First of all, it's very strong, but it's a partial order, meaning that it's not always possible to compare two vectors, right? Maybe for some pairwise difference, it's going to be smaller for one, then some indices it's going to be smaller for the other. It's not necessarily true that it's always the case, that you can always compare. And then we're going to say that a mixed auction delta dominates another one in pairwise difference delta prime if this holds true almost surely, basically. And by the writing I did of the winner's empirical variance as pairwise difference, I have that if I have that delta dominates delta prime in pairwise difference, I have that delta has a lower Wiener's empirical variance than delta prime. Okay. And also you can take any other metric you want instead of which is increasing in the absolute value. So maybe instead of looking at the square difference, you can take like the absolute value difference, or maybe you can look at the range, the maximum of the UI minus the minimum of the UI. Every kind of thing like this is going to work. Okay, so this is a notion, and as I want to emphasize, you don't always have a comparison possible between two options. So this is just a partial order. Okay. So now let's get into the results. And maybe like if you've fallen asleep, this is the time to wake up again. So we have that uniform price auction is dominant in pairwise difference if and only if you have a pure common value. Okay. So the if part is very easy because if you're pure common value, this means that the VI for every winner is the same. And if you're uniform price, this means that the PI for everyone is the same. So if VI minus PI for everyone is the same, the utility is the same for everyone. And so if you look at the pairwise difference, it's going to be 0. And if it's 0, it's obviously optimum because it must be positive. So this direction is very easy. The other direction is a bit more subtle. It's saying that actually, if you have just a little bit of private part value, you know that uniform price is not going to dominate. And this is this is a bit technical. So this is just due to the monotonicity properties of the equilibrium we derived before. So basically, you can show that the winner's empirical variance can be smaller if you add some price discrimination when you have some private value part. Okay. And in particular, this means by the continuity of the winner's empirical variance in delta and C, that you always, for any distribution, you're always going to have a range for some C star between C star and 1, for which some mixed pricing is optimal. So some mixed pricing is better than uniform and better than PSB, right? So these are two statements. I'm saying that the first intuition we had, which is that there is a typo. It's like 1 open, like 1 not included. Yeah. So if so the first intuition which was pure common value is the best, sorry, uniform is the best with pure common value is true. And the fact that mixed pricing is always useful is also true. Okay. And then we go to the last intuition, which is, so intuitively we expect that the PSB has always lower winner's empirical variance than uniform pricing for private value, for kind of the same reason that I outlined before, like when I showed the example. So let me just show this briefly again. The idea here why you have smaller pairwise difference for the private value is even if you have a very high value, because the equilibriums are increasing, you're also going to pay more. And so the gap between your utility is going to be smaller when you are in the PSB rather than the uniform. Okay, because basically, yes, like here you see that the price, higher the value, the higher the price, whereas here the value the price stays the same. So if you compare people which have like from small value to high value, if you want to have to smaller discrepancy, you want to have like price which increases as well. Okay, so this is intuition. And now you can kind of forget about what I just told you because this is false. Actually, you can have distributions for which the winner's empirical variance is smaller in uniform price compared to PSB. And this is very counterintuitive. And actually, I think we tried to prove that this was true for 1.5 months before thinking, actually, what if it's not true? You know, so just to tell you that sometimes numerical experiments are good to try to check your intuition. And the idea, I'm not going to go into detail of the construction of the counterexample, but the idea is if you have a bidding function, let's say this orange curve, which is very steep, what can happen is that as your signal increase, your utility is going to decrease given that you have one item. And this is given that you have one item, which is very important. Because here, so the red curve is basically my utility for a signal of 0.5. And the purple segment is my utility for 0.9. And you see that here, as I increase my signal, between some realizations, my utility is going to decrease. My utility is not going to decrease in expectation overall, because otherwise this would not be in equilibrium. But just given that I'm winning, given that I'm already guaranteed to win, basically, my utility can decrease if my bidding function is very steep. Okay. And so then you have to construct a counterexample, and this is very, very annoying because first of all, you know that the bidding function at the origin has a slope of at most 1, right? So this is actually quite tame. And then if you want to say, okay, have this bidding equilibrium, and I want to like take a distribution such that the mass concentrates around the part where I'm very steep to ensure that the expectation is high. If you move the distribution, then you're also going to move the bidding function. And so then maybe it's not steep anymore, right? So that's why it's difficult to construct a counterexample. But basically, the idea is you want to construct a distribution such that the bidding function doesn't move too much as you like put all the mass onto a single point. Okay, so this is the idea. And so this means something important is that if we want to get any results on the Wiener's empirical variance, we need to restrict the space of distributions, right? We're not going to be able to get anything if we just consider all distributions in generality. Okay, now let me give some of the main results. So first of all, we're going to work with, so the space of distribution we're going to restrict to is log concave densities, log concave distributions. And they're very common in the literature, in economics literature, in many, many places. This includes a lot of common distributions. And we say that a distribution with density f is log concave if log of f is concave. So it's not the craziest definition with respect to the name, but it has very, very nice properties, which is that it's closed under multiplication, meaning that if you have f and g log concave, then fg is log concave. It's closed under marginalization. So this I'm not going to get too much into, but it's also closed under integration, meaning if you have the function, the density f, which is log concave, you also have that the CDF f is log concave, and you also have that the integral of the CDF is log concave. So you have kind of this nice like closure properties, which are very useful because now if you want to look at the CDF, if you want to look at the order statistics, so the order statistics is basically you have n signals, and let's say you want to look at the distribution of the maximum, okay? Or let's say the distribution of the kth maximum. So the distribution of the case, the density of the case maximum can be expressed as this stuff. So like this product of f, capital F, 1 minus f, etc. Right? And so if you know by properties, so f is log, so now if you have that f is log concave, right? So the integral is log concave. Then you take a power, it's a product, it's still log concave. You have 1 minus f, which is log concave. So everything is still log concave. And then you can apply against the closure property. Overall, you have that the order statistics are still log concave. And this is where the statistics are log concave. This is kind of the crucial technical part. And because using this, you can show that if the integral of the order statistic is log concave, then you can bound the slope of the bidding function for the specific case we have. So you can show that it's smaller than 1. And you can recover kind of the natural, like kind of concave shape on the bidding function. And this is also the properties of order statistics, which I'm not going to get into. But I just want to make another comment is you could get also some kind of bounds on this bidding function by imposing some convexity or concavity conditions on the integral of the order statistics, right? But the nice thing about this result is you just need to put these restrictions on the density of the original signals, and then you get it all the way back from to the integral of the order statistics. Whereas if you put like some other concavity conditions, you would not necessarily get this, right? So this is why like log concave distributions are very nice because they behave very well, and like they're also closed under convolution and stuff like this. Okay. All right. And so now one of the main theorem is, so you assume that the signals are drawn from a log concave distribution. Then for a given value, private value proportion 1 minus c, you know that the auction with price discrimination 1 minus c pairwise dominates all auction with a price discrimination less than 1 minus c. So basically you fix any c, so on this graph, okay, you fix any C, and you know that the one on the green curve is actually going to pairwise dominate all of the ones below. Okay, so this is very strong because this says this is in pairwise dominance, right? So this was not even necessarily true that you could compare this, but I'm saying actually if you have log concave signal, this is true. And this recovers our original intuition because if you look at the far left here, you see that the top point here on the top left corner pairwise dominates all those below. So this means that for pure private value, pay as bid is optimal in terms among all the mixed auctions. Okay, so so if basically the message is the intuition usually is not true, but if you impose this log concave condition, which is in some sense necessary, you can recover the intuition. And so some example of distributions for which it is true, you have like normal, exponential, blah, blah. You have a lot of them. Let me just give also an alternate version of this theorem, which says that basically any auction in this green zone, okay, pairwise dominates the uniform auction. Okay, so this is just an alternate stuff, so which means that even if you have some common value proportion of C equal 1/2, you still have that pay as bid is better than uniform. And so here is the graph of the optimal wave, like for an example graph for uniform distribution of optimal wave. And you see that for a long time, actually, the optimal one is pay as bid. Okay, and so it's optimal for exactly C equals 0. So this is correct with the theoretical results. Then you have this region where, as I was saying, mixed pricing is useful, and at the end you get back the pure common value case, right? So here you can kind of see like first you have pure private value, then the transition, and then pure common value. Okay, and so now let me finish by maybe one of the most surprising result, I think, and which is also really interesting, I think, is okay. So I've looked about mixed price auctions, and now I want to consider all auctions, all possible auctions, and I want to think about, does there exist a mechanism that always dominates in pairwise difference all other mechanisms? Okay, so I'm basically saying, is my space of auctions a semi-lattice according to this partial order? Okay. And what is the lowest winner's empirical variance that you can achieve? And the reply to this is yes, and it's exactly 0. So the thing at the beginning, which I said, you cannot just like take the surplus and distribute it, and it's not going to work because people are going to strategize. You can actually do this by using a very specific payment function, because basically, so everyone is going to bid truthfully. You're going to look at the profits. You're going to redistribute it, and the only thing which you need to ensure is the incentive compatibility. Okay, this is like the real hard part, and it's not even clear that it's possible to do. Like we didn't. It was possible actually to get 0, and so this is the payment function. So it's kind of ugly, and it's normal. So G is the order statistic. It's the CDF of the order statistics of the kth highest value among n-1 values. So small g is the density, and y is the first rejected bit, basically. And so you see that if you have this following payment scheme, okay, and this is in some sense close to the mixed price auction, but it's like it's not a convex combination anymore, right? So you have like this SI is kind of the private part. This V is kind of like the pure, like the first rejected bit part, and then you have like these extra terms, this minus, which are quite weird. Then this mechanism is actually perfectly equitable and incentive compatible, meaning that regardless, so I want to emphasize this, regardless of the signals of everyone, for each realization, every winner is going to get the exact same profit. Okay, so this is, I mean, to me, this is very weird. This, like, if you try to think about it, it means that regardless of if you have your very high signal or very small signal, you're going to get the same profit as everyone else. It doesn't mean that for every realization, the profits are going to be the same, but given a realization, among the winners, the profit is going to be the same. And just to really emphasize that this payment is very weird. So this is the payment, okay? So let's say that you have only two players, okay, and Y is basically the signal of the other one. And so if you have a signal of 0.2, okay, you're actually going to pay 0 if the other one has the same signal as you do. So if you have a low signal, if you win and the other one has also low signal, then you're going to pay 0, okay? And even weirder, so if you look at closely at the y-axis, it's not a mistake. It does go to the negative. So if you are a winner with a very high value and someone wins with also a very high value, you're going to receive a negative payment, which means you're going to get money from the auctioneer. Right? This is weird. This is weird, but overall, it remains fine because basically in other situations where these weird things don't happen, you're going to be like incentive compatible. And so I want like this auction has the same revenue as the other ones. Okay. This is revenue equivalent. So there's no issue with that. Same revenue. Everyone is equitable. It's incentive compatible. And the idea is basically when you have two winners, okay, if you have a very high value, if you win with a very high signal and the other one win with very low signal, then you're both going to pay a lot in some sense. Okay, but if you have the same signal as the other winner, then you're going to not pay a lot or even win money. And the idea basically is if you want to avoid like this dispersion of profits, you have to correlate the payments. And you have to think about these bonuses to ensure the incentive compatibility. Okay. And by the way, if you look at C equal 1, this was for pure product value, right? If you look at C equal 1, you just have a straight line because we know that for this case, the uniform auction is optimal, right? And I mean, like if the auction is very unlucky, he's going to have to pay a lot for some realization. It can even go to minus infinity. But because he gets more money on other case, and by revenue equivalence, the revenue of the auctioneer is going to stay the same. So overall, I think I went a bit over. Sorry about this. So overall, we initiate the study of surplus and equity in auctions. Okay, we think about what does it mean about equity, and so we introduce some model where we can have some tractable results. We give some intuition and some comparison results on prior free or at least among log concave distributions between pay as bid, mixed pricing, and uniform price auctions. And then we derive the equitable the perfect equitable incentive compatible mechanism. But this time it does depend on the distribution, right? So if the auctioneer does not know the distribution in advance, it's not a prior free result. So it's why like both of those results are interesting. So thank you very much, and I'm happy to take questions.
So thank you very much, Mathieu, for your very interesting talk. So are there any question? Maybe I can start because I have some maybe naive question, but the first thing is that like at some point you said it like you said, well, in the sense that you said that there are some signal involved into the kind of into your auctions, and I don't understand how signals are linked with the kind of simultaneity of your auction that you're looking at. Have I missed something, or because I guess there's a learning process involved somehow, and I have not fully understood
So what
is
happens
inside.
is that let's think about let's imagine you want to have you want to drill some oil, some gas. Let's not be environmental at all. And you have this kind of spec, and basically the value of the oil that there is in this well, it's the same for everyone, right? Because there is a fixed quantity, it exists, and it's the same for everyone. So this is a case of common value. However, maybe because your company made some measurements, you have some kind of information which is related to this common value. So these are the signals, right? So you can assume that everyone has some information, some signal, okay, with which they're going to bid. So they think about, okay, so I have this signal. I know then that the value to be roughly this, right? And I'm going to bid this quantity. And then you receive then so you bid, everyone bids simultaneously. The auctioneer just look at the bids and give the item to the highest bidder.
Okay. And so whenever, okay, I understand. And therefore, like you said, like basically what you see on the auction point of view, you have you see the signals, you see the bidding, and are you trying to estimate like the kind of the signal that you have? Are you actually computing this delta? I understand like theoretical, if you were to be like equitable, like you would need to have you would need to like pay with the certain with this certain convex combination between like these two strategies. But so would you be able to do that? And if so, wouldn't be complicated somehow? In the sense that I think that whenever you engage in an auction, you will must say how what are the how the auction works before then actually engaging in the auction. So I don't know like if my question makes sense and how to solve the problem.
Definitely makes sense. And that's why, this equitable mechanism has the fact that you need to know the distribution of the signals, right?
Yeah.
This is for sure. Um, and like so like let's say in the prior free results, like if you are pay as bid or uniform,
Hmm.
the idea is the only thing you have to fix is the delta.
Yeah.
Okay. Then if the bidders themselves know the distribution and know the signals, then they can play. And you at the auctioneer, once you fix delta, everything is a function of the bids or all of the thing you're going to pay, etc. So you don't necessarily have to learn the signals in this case, like if you do first rejected bid, etc. You don't have to do anything. There is some stuff which can be done, like there is question in auctions about a learning aspect, where like, and I'm going to take a simpler setting, okay, where we have single item, private value, etc. One thing people do sometimes is you play a second price auction for sometimes. So people are going to bid truthfully because it's a second price auction, right? And so from there, you're going to get signals, right? From this, you can compute the distribution. And then maybe from there, you can compute the optimal auction in some sense afterwards.
Okay.
Like
But when you change the optimal option, wouldn't like the signal change as well?
so the signal wouldn't change because if the distribution stays the same, if the distribution of the value you have
Yeah, okay. Yeah, you're right. Sorry.
stays the same, but the utility, like what you're going to bid is going to change, but you don't care about it because you already took that into account with the auction process.
Okay. Okay, okay.
And
So thank you.
basically that works. I mean, it's not related to this, but when you want to do like a VC dimension before function, to say that you can learn like empirical auctions quickly or something like this.
Okay. And maybe the last question, like then I will like we can wrap it up. Like the thing is,
Sorry,
can you
Antonio.
go beyond? Bye, Filippo.
Sorry,
Can you go
Antonio.
be
We have to go to another seminar. So sorry, I have
ah,
to leave.
don't worry, it's fine. Thank you, Filippo. Bye
Sorry.
bye.
Thank you for the talk. Bye bye.
Goodbye.
Can you go beyond low concavity?
Oh no no.
Okay, this is a
Oh, no,
very,
no,
very
no,
much
no, no,
open
no.
question.
I mean, this is kind of related to something I mentioned briefly at some point. Is you can try to like log concavity is a form of like generalized convexity or concavity. It's like if you do concavity and on left side you have like arithmetic mean and on the right side you have harmonic mean, right? This is actually equivalent to log concavity.
Mm-hmm.
Think about okay now if I do like arithmetic mean and geometric mean on the right side, you're going to get all the bounds on this, but this is only if you put those conditions on the integral of the CDF,
Mm-hmm.
which is not really reasonable
Yeah, okay.
because it changes too much. Like it's basically saying, oh, given the result, I have the result. It's
Yeah, no, I understand. I understand.
that's
Okay.
yeah, log concave for now works well. So one thing which like there is a class of distribution which is monotone hazard rates, which might work because it's classical in auctions as well. It's like you want the density divided by the CDF to be increasing or something like this. Okay. And
Okay.
actually, log concave implies the molten hazard rate. So this would be nice, but I have no idea how to technically get anything.
Okay. Well, thank you very much. And maybe you can wrap it up. So thank you again, Mathieu, and stay tuned for another session of Surfing the Ocean. Bye bye.
Goodbye, everyone.